Hello, welcome to a podcast on bonding. Bonding is a process where atoms try and seek stability. They try and be stable by losing and gaining electrons, ionic bonding, or sharing electrons, covalent bonding. In this process, they are trying to act like noble gases. So if you can nickname bonding something, you can nickname it the noble gas wannabe game. Atoms do this in two ways. They either give and take electrons, that's a metal and a nonmetal, and we've talked about this at length, and this is called ionic bonding, where there's a loser and a gainer. The giver becomes charged positive and the taker becomes charged negative. Or, as we're going to start learning today, atoms can come together and share a pair of electrons to become stable in something called covalent bonding. And we're going to learn about that and the rules of how that exists. So far, what have we learned? We've learned that with ionic bonding, it's a game of give and take. There's a loss and a gain of electrons between a metal and a nonmetal. Metals become charged positive, nonmetals become charged negative, and the fancy word for that is cation and anion. If you'll notice, there's a plus right in the word cation. C-A-T-I-O-N. And that tells you that these are metals, or they become charged positive. And anions, the word negative is right in there. See that? So the fancy word for negative ions, a negative ion, is an anion, or an onion, if you like to remember it that way. Now, we've drawn Lewis dots. Lewis dots for atoms and for ions. You've learned that Lewis dots represent valence electrons. And these valence electrons can be found by looking at the top of the periodic table. And in sodium's column or family on the periodic table, there's one dot, one valence electron. For chlorine, there are 7. And I'm actually going to go ahead and change colors for sodium so that we can follow what happens to it. On the periodic table, the valence electrons are listed as they are as atoms. Sodium would love to lose this electron, and chlorine would love to gain an electron. Chlorine needs to have 8. It needs to have a stable octet. And so does sodium, but you don't really see it. We'll talk about that in a second. So this sodium right here loses its electron. So I'm going to go ahead and show you what happens. This gets lost, chlorine gains it, and this electron isn't here anymore. So we don't draw it like that. We put brackets around sodium and put a positive 1, signifying that it lost an electron. And chlorine gets a bracket around it with a negative 1, and this is why. It gained that electron from sodium. Along with its other 7, it now has a stable octet. These are ions, positive 1 and negative 1. They form what's called an ionic bond because this one loses, this one gains, and they attract each other. And the whole charge of the whole compound is 0. And you've written it as NaCl. Now, let's look at this in terms of electron configuration and orbital diagrams. Electron configuration is this 1s2, 2s2 stuff we've been doing. And the orbital diagrams are the up-down arrows that signify the electrons that have gone along with what we're doing. Okay? So, let me erase this. And let's go ahead and draw the electron configuration and orbital diagrams for sodium and chlorine as atoms and then as ions, so you can start getting a deeper perspective of what's going on. Sodium has 1s2, 2s2, 2p6, oops, I can draw 3s1. Now, if you look, it has 1 valence electron. If it got rid of it, it would have a noble gas configuration on the floor below. So it's almost like this is very irritating for it to hang on to. It would love to get rid of it. Chlorine has electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. Its valence level, its outside energy level, has only 7 electrons. It would love to gain an electron so it can act like a noble gas. It doesn't change. Sodium still has the same number of protons, and chlorine still has the same number of protons. But when it loses this electron, it becomes charged positive because the negative charge goes down by 1. And if this gains an electron, this charge of chlorine goes up by 1, and so it becomes charged -1. If you look right here, here's your 8. 2 and 6 is 8. That's the stable octet. 2 and 5 is 7. If this electron gets added over here, then guess what? It's stable. So I'm going to go ahead and draw for the sodium ion and the chlorine ion here. I'm going to draw the electron configuration and orbital diagram. Okay? So for sodium, it's 1s2, 2s2, 2p6. Up, down, up, down, up, 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 down, down, down. If you notice, its valence level is full. It acts like a noble gas. Okay? That's neon. It acts like it. What does sodium become charged? Sodium becomes charged +1. Why? It lost this electron. Where'd it go? It went over here. Okay? So on the chlorine side, let's look at chlorine. Chlorine is 1s2, 2s2, 2p6. I'm going to draw this so we don't get behind here. Oops. I'm sorry. I'm breaking Hund's rule. Okay. 3s2, 3p5. Up, down. 1, 2, 3. 1, 2, 3, 4, 5. That's how many chlorine normally has. But guess what? It's gained an electron. It gained an electron from sodium. It has 1 extra electron, and so therefore it's charged -1. They balance out. So look at this. This has 3p6. 3s2 and 3p6. The noble gas it gets to act like is argon. They're both happy, they're both stable, and they do this losing and gaining thing called an ionic bond. Now why is this? Well, there's a fancy term called electronegativity. We're going to start poking away at this word a little bit so you feel comfortable with it. And electronegativity is nothing more than the pull of the nucleus on the valence electrons. Think about what lives inside the nucleus. Protons. And it pulls on all the electrons, but we don't care about the inner electrons, we care about the outer electrons, the valence electrons. They're the ones that take place in bonding. And if you'll notice, this right here is a scale of electronegativity, and fluorine has got the highest electronegativity value on the periodic table. The noble gases aren't even listed. What do you think their electronegativity, their pull on their valence electrons is? Yeah, you're right. Pretty darn high. That's why we don't even list them. That's why we don't even play this game. They're stable. Their energy levels are full. Why share? Why lose and gain? So if you look, fluorine has a value of 4. It's a gainer, isn't it? We already said this from way back in the beginning. These gain. Fluorine gains the best. So where are the losers? And why do they lose? Well, if you look right here, the losers are over here on the metal side. The middle of the periodic table is not there. Okay, it's kind of to just show you the trends here. So if you look, that's the lowest value. It's a loser. This whole side is losers. Look at it. This tells you how well it hangs onto an electron. 1.9. It gets worse as you go down, doesn't it? What happens as you go across? Ooh, it gets better. That's because these gain and these lose. Now if you'll notice something real quick, hydrogen's here. The only reason hydrogen is here on the periodic table is because it is in the alkaline metal family on the periodic table because it has 1 valence electron. It's not really part of the alkali metals. The alkali metals are a completely separate group. Okay? The only reason hydrogen is here is because it has one electron. If you look closely at the periodic table, hydrogen should really be right around here somewhere, shouldn't it? We're going to keep that in mind. Here's a nice chart that kind of shows a trend of electronegativity, which again measures how much an atom attracts electrons to itself when it's bonded with another atom. Look how high this is over here. No wonder these gain. The love of their nucleus for the electrons is so high that they want an electron badly. These over here, they don't need an electron. As a matter of fact, they like to lose. It irritates them. Look at hydrogen. Here's hydrogen. It doesn't fit in here, does it? Okay? That's why it fits more in this area. So on your periodic tables, hydrogen is listed in a bad place for bonding, but a good place for valence electrons. What's the difference? Ionic bonding, there's a big electronegativity difference. And covalent bonding, there's a medium to no electronegativity difference at all. Let's look at this for a second. Metals are over here, they lose. Nonmetals are over here, they gain. And so if you look, these have a lousy pull. These have a super duper high pull. The bigger the difference between a nonmetal and a metal, oops, I shouldn't put that, sorry, and a metal right here. If you have this combining with this right here, that's a huge difference. Look how far apart they are on the periodic table. We're actually going to do math and subtract them. The bigger the difference, you have an ionic bond. A loser and a gainer, a positive and a negative. But what happens if something in here starts to combine? The electronegativity values are very close to each other. See this? The difference isn't as big. You have 3.0 and 4.0. Not that much of a difference. Versus 0.8 and 4.0. So rule of thumb is very far apart is ionic, and closer together is covalent. Let's just plant that seed for right now. We'll come back and do some math in it later. Okay? So this is a metal and a nonmetal far apart, and these are closer together. And remember, hydrogen's in there, and hydrogen really should be on the periodic table right about here. And in the front of my room, I've put hydrogen right above boron on the periodic table on purpose. Okay? As far as electronegativity values. Bad periodic table, sorry. But over here are the metals, here are the nonmetals, gainers, and losers. Hydrogen again should be right here. Okay? So let's talk about covalent bonding, or sharing a pair of electrons. This takes place between two nonmetals, so it's typically in this side of the periodic table. It also occurs between a hydrogen and a nonmetal, and we just talked about why hydrogen should be here, because it's got an electronegativity value of about 2.1. This is a value of about 2, and this is a value of about 4. These are like 1 and down. It doesn't fit here. The only reason it's here again is because it has one valence electron. So hydrogen takes place in covalent bonding. Here's that scale again. Okay, see why it doesn't fit here and why it needs to move over here. Now, you've already written these rules down. I'm going to shut this right here and move this over here. I'm going to talk to you about it real quick. We need to determine the total number of valence electrons for all the atoms. We're going to do these step by step with examples. That's step 1. Step 2 is to draw a skeleton structure. If you have a skeleton of a bear, you know it's a bear versus a mouse or a cat. So you can draw a skeleton structure. A line like this is going to represent 2 electrons. The shortest distance between 2 points is a straight line. So instead of drawing dots like this, and I can do that, but we're not going to do that. We're going to draw a line because this represents a shared pair. And whenever you see dots like this, it represents a lone pair. Okay? Just hang on for a second. We're going to reinforce this. That's step 2. Draw a structure and connect them with a line. Step 3, all these valence electrons we've added up here, we're going to go ahead and arrange around the rest of the atom so that all the atoms are happy or stable. They all have a stable octet. Hydrogen has a duet. How come? Look at hydrogen. It's on the first energy level. It has 1s1. The most electrons it can hold is 2 for a total of 1s2. It can't fit anymore. Or let's go back to your bad Bohr model. You can only put this many on the first energy level, right? And so that's why hydrogen can only have 2. Step 4 we're really not going to go into today, but just know that if they're not stable, and we've done 1, 2, and 3, we're going to have to rearrange. But that's not for right now. We're going to do the basics first. So moving on. Let's learn how to draw these. Step 1. We're going to go ahead and try and draw hydrogen, H2. If you look at the periodic table, each hydrogen has 1 valence electron, and so 1 plus 1 for each of them equals 2. Next, in step 2, we're going to draw the skeleton structure. If you look, there's 2 hydrogens. That means I'm going to draw an H and an H, and my next step is connect them with the line. How many does that represent? It represents 2 electrons. So I'm going to go ahead and say there's 2 electrons here for this hydrogen. Step 3 says to arrange the rest of the valence electrons around the atom so that they're happy. Well, how many valence electrons does hydrogen bring to share? There's a total of 2. How many have I drawn here? There is a total of 2 electrons, aren't there? So now comes the part that is confusing to some kids, but think about it. Think of this like a pencil or a rope right here. This shared pair. It's shared. This hydrogen is going to use this pencil or this bond, those 2 electrons, and we're going to see if it's happy. Remember, hydrogen, each hydrogen needs 2. Does it have 2? That line represents 2. Well, what about this hydrogen? This hydrogen also has 2. Okay? That line right there represents those 2 electrons. Erase this. Make it a line again so you can keep track of that bond. Sorry, change the color, but you get the idea. Okay? So this hydrogen over here has 2 electrons also. Why am I double counting it? Well, think about it. If I have one person and another person, and they're each sharing a pencil, there's only one pencil, right? Okay? That pencil right there, that bond that they're formed or they're sharing, is getting counted twice. This person uses the pencil, and this person uses the pencil. They're both happy. That pencil represents 2 electrons. This line represents 2 electrons. Each hydrogen's stable. It's happy. And so that's how you draw the Lewis dot structure for a covalent bond between hydrogen and hydrogen. Let's go ahead and draw it for HCl. This is the compound hydrogen chloride or hydrochloric acid. The first step is to determine the number of valence electrons, and if you look on the periodic table, hydrogen has 1 and chlorine has 7. So if you add 1 plus 7, that's a total of 8 electrons. To have a Lewis dot structure for a covalent bond between hydrogen and chlorine, you need to use all these 8 electrons. My next step, you're right, is to draw H and Cl and connect them with a line. How many does that represent? If you said 2, you're right. Okay, and so I'm done with step 2. Step 3, I need to arrange the rest of the valence electrons. These elements, hydrogen and chlorine, brought a total of 8 valence electrons. That means that I have to take these 2 and either on paper or mentally subtract, and I have 6 electrons left to distribute. Now, can I put any more around this hydrogen? I can't, can I? How come? Hydrogen needs how many? Hydrogen needs 2. Does it already have 2? Oh, it does. Okay? So, therefore, what I need to do is I need to draw the rest of the electrons around chlorine. I have 6 more to distribute. I'm going to put them around in pairs. There's 2, there's 2, and there's 2. Now, let's go back and make sure I've drawn all these 8 electrons so I can cross that out. Have I? There's 2 there. 3, 4, 5, 6, 7, and 8 total valence electrons. I'm done drawing. Now my next step is to check and make sure it's stable. Is this a stable compound? Indeed it is. Looky here. This chlorine has how many electrons around it? 2, 4, 6, 8. That makes it happy. It has to have a stable octet. How about that? And what about this hydrogen? Well, we already determined this hydrogen was stable up here, didn't we? Right? It has 2 electrons too. Remember, we're double counting it like a pencil, like a rope, like a bond between it. And so therefore, this is a stable Lewis dot structure for the covalent bond between hydrogen and chlorine. Let's try another one. We're going to go ahead and draw, oops, sorry about that. We're going to go ahead and draw F2. Fluorine is in the halogen column, so it has 7 plus 7. That equals 14 valence electrons that it needs to distribute between fluorines so that it's stable. My skeleton structure is F line F. That line represents 2 electrons. Remember, these are only the valence electrons. Now we're going to arrange the rest of the electrons around this structure. If you have 2 that you've drawn, subtracted from 14, that's 12. Not all you need to do it like this on paper. Try and do it mentally. Okay? I have 14. I've used up 2. How many do I have left to draw? 12. So I'm going to go ahead and draw fluorine, fluorine. And you don't need to redraw this when you start doing this, but I'm just showing you step by step. I need to put 2, 4, 6, I'm going to count that, 8, 10, 12, 14 total valence electrons around there. See that? I've drawn all 14. My next step is to make sure it's stable. Is this fluorine happy? Does it have a stable octet? Yes, it does. It has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. How about this one? Looky here. 2, 3, 4, 5, 6, 7, 8. I've drawn all 14 valence electrons in a game of bonding called covalent bonding. This is a shared pair right here. This is a shared pair. And all these other pairs right here, 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 and here, all around there, are lone pairs. They together make a stable covalent molecule. Now, things get a little bigger, obviously, because not all molecules are tiny. So we're going to draw 2 more. Okay? We're going to draw NH3. And NH3 has 5 plus 1 each for the hydrogen, so it's a total of 3. So I bring 8 valence electrons to this relationship. This is ammonia, by the way. In an ammonia, I'm going to put nitrogen in the middle. Now let me just show you something for a second, because you haven't drawn these before. Maybe you think it looks like this. Why not? Why wouldn't you think that? I mean, there's a nitrogen and there's 3 hydrogens. Can this work for this hydrogen? Nope. How come? Hydrogen has 2 and 2 is 4. It can't have 4. How about this hydrogen? Nope. 2 and 2 is 4. It can't have that, right? Remember, hydrogen needs a duet. Okay? So we're going to go ahead and get rid of this. Okay? And I'm going to draw NH3. It was a total of 8. 5 plus 3 is 8 total valence electrons. And a lot of times, if it's not hydrogen, the very first one is the center of attention. So I'm going to go ahead and draw it like that. It doesn't matter if I put a hydrogen up here, you know, and don't put one over here. It really doesn't matter where I put it. Okay? But I'm going to go ahead and draw it like this. How many electrons have I used? 2, 4, 6. I have 8 to draw, don't I? And that means I need to put 2 more. Each of these hydrogens is stable the minute I put it there, remember? Because it has a duet. Now I'm going to go ahead and put a pair of electrons up here. That's a total of 8. Let's check. 2, 4, 6, 8. Yep. Each hydrogen is stable. 2, 2, 2. How about the nitrogen? Look at that. It has 2, 4, 6, 8 electrons around it. So the correct way to draw ammonia is to draw it like this. N, H, 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 with 2 dots up top. These are all shared pairs. They're shared back and forth in a tug-of-war between nitrogen and hydrogen. And this pair up here is a lone pair, and in reality it forms this huge blob up here. Lone pairs bend molecules. Ooh, that's not a big sorry about that. Lone pairs right here bend electrons. They bend a molecule. They push down on these right here. Okay, so there's shapes involved. We'll talk about that later, and it actually bends this one down too. But that's another time. How am I going to draw CH4? Center of attention, right? This carbon has 4 valence electrons. Each hydrogen has 1. There's 4 of them. That's a total of 8. They need to share them to be happy. Draw the carbon. Draw 4 lines because I got 4 hydrogens around it. Have I drawn all 8? Let's see. Each of these hydrogens is instantly happy, right? Because it has a duet. 2, 4, 6, 8. Well, that hydrogen's happy, that hydrogen's happy, that hydrogen's happy, and that hydrogen's happy. And look, this carbon's happy too. 2, 4, 6, 8. Stable. How about that? So this is the structure for CH4, drawn like this, and it's nice and happy. It makes a tetrahedral shape. You don't need to know that yet. Okay, where this bond actually sticks out at the board at you, and this right here goes back into the plane of the board. We're going to build these so you can see that. One last structure we're going to try today is water. H2O. You tell me how many valence electrons hydrogen has. Right. Hydrogen has 1 plus 1 because there's 2 for a total of 2. How about oxygen? Oxygen has 6 valence electrons. Not 8 like in its box. That's its total electrons. 6 is valence at the top. This needs a total of 8 to be happy, to be stable, to share. We've done step 1. Step 2 is to draw the skeleton structure. Now remember we said right here, if we drew it like this, like it says to, H2 and then an O, there's something wrong with this. We can't draw it because this hydrogen cannot have 2 and 2 is 4 electrons around it. It needs a duet. So you know that's wrong. So water is written the way it's written, and you're going to have to remember that hydrogen has to be on the ends. So therefore, the symbol or the structure for water, let me change that color, sorry, is this. Oxygen in the middle. I'm going to draw bonds. Okay, put hydrogens on the outside here. Now, how many valence electrons do I have to draw? 8. How many have I put here? I've put 2, and 2 is 4. I have 4 more to draw, don't I? Because 8 minus 4 equals 4. 4 left to draw. I can't put any on these hydrogens. The minute I put these lines here, hydrogen's stable. The only place I have left is to put electrons in pairs around the oxygen. Have I drawn 8? Let's check. 2, 4, 6, 8. I only had 8 to draw. I'm done. Okay? Now, let's get rid of this so it's not as messy on here for you. Hydrogen's happy, right? We agree with that because each hydrogen has 2. This hydrogen has 2 also. What about oxygen? Well, looky here. Oxygen has 2, 4, 6, 8 around it. So I've drawn all 8. They're sharing. Everyone's nice and happy. And this is the Lewis dot structure for water. It does not show the shape. Can you find the shared pairs and the lone pairs? This is a shared pair, isn't it? This is also a shared pair. Where are the lone pairs? Right, the lone pairs are on oxygen. And if you look, what do? They're like fly wings, okay? They take up a lot of space, like this, and they're going to bend this molecule. And again, we're going to build those in class, and there'll be another podcast on that. Now you try it. You have a paper in front of you that you need to work on, and then we're going to come back to class and we'll build. Hopefully this has helped you, and if not, you can come in and ask me questions. Have a good day.